Okay, kiddos. So, here's a video lesson describing Newton's law of universal gravitation. This is the means by which we can calculate the gravitational force between two objects. So, we are used to gravity being the Earth pulling on us because the Earth is actually the only huge mass that we are close to. But if you think about it, we do experience gravity from the moon. That's what causes tides. And we do experience gravity from the sun. That's what keeps Earth in orbit around it. So we do feel the pull of those big objects, but mostly only Earth. So Isaac Newton created this law, which is actually we'll use it as a formula that describes the gravitational force between two objects. The story goes that an apple fell on his head, and so I like this illustration or painting or whatever. It looks like we have an apple in the background and the moon. The story goes that an apple fell on Newton's head, and he came up with the bright idea that, oh wait, instead of a question mark, this should be a light bulb. And he came with the bright idea that the forces that act on the apple falling to the earth are the same as the forces that act on the moon, keeping it in orbit around Earth. We'll also study the prism and that kind of thing. But this is why the law is named after him. So we have two objects, such as the moon and the sun, and they are going to attract one another with some force. That force is we have F equals G m over r squared. So in this formula, this is the gravitational force between two objects. You feel no, you don't feel it. You experience a gravitational force with the person next to you, or the desk you're sitting in, or the car that's in the parking lot. But it's so incredibly small that you don't actually feel it. So this is a constant. Big G is called the universal gravitational constant, and it has a value of 6.67 times 10 to the negative 11th. So this is a very small number, 0.000000, etc. Meaning when we take two masses and we multiply them together, we're going to get some force, and the force is pretty small. M and M, candy, refer to the two masses that are actually attracting one another, and then R is the distance between them. So let me draw a little diagram here. So we have some big mass and some littler mass, and between them, so the distance from the center of one to the other would be R, and that would be measured in meters, and the masses would be measured in kilograms. Alright, so there it is. We'll do a sample problem on the next slide. So let's suppose that you go bowling, and I don't know, 4-kilogram bowling ball, and your buddy's really into baseball, so you have a 1-kilogram. That might be pretty heavy for a baseball, but we can pretend. So let's see. Baseball looks like this, and bowling ball looks like this. Alright, and you set them down. You go to the bowling alley and you set them down, and they happen to be about 1 meter apart. And so you see this and you go, hey, this is just what we're doing in physics class. Forget bowling, let's do some calculating. So this is the way it would go. The gravitational force between these two objects. And you say, what? Gravity between a baseball and a bowling ball? I don't believe it. Yes. We'll calculate it. The force will be very small. So the force ends up being big G, 6.67 times 10 to the negative 11. It's called the universal gravitational constant because it is always like that. And, I mean, it's the same for all mass in the universe. And then we multiply one of the masses by the other mass in kilograms. And we're going to divide by the radius squared. So this is actually not too bad because all these ones are going to cancel out. 6.67 times 10 to the negative 11. And I should have calculated, I can use my phone. So 6.67 times 10 to the negative 11 times 4 will give us, pause while I find my calculator. My old eyes can hardly see. 6.67 times 4 equals, okay. And so we would get 27.68 times 10 to the negative 11, which, to be correctly in scientific notation, would be 2.6, and I'm going to round here, and that would be times 10 to the negative 10, because we moved the decimal one spot. The units would be newtons, and you see that's a pretty small force, where we have, we'd be going 0.00000000000, definitely sort of immeasurable by any standard means. So that's an example of how to calculate gravitational force between a couple objects. I think you have some questions to practice, and we'll get more into sort of the meaning of the fact that the radius is squared, and so we talk about this inverse square law and all that kind of good stuff. But there are the basics of the equation, and good luck.